Hey everybody, let's look at section 2.7 today. In this section, what we're going to do is going to sort of take what we did last time, where we're now finding the big word derivative, but now we're going to find it for all values of x. So we're going to leave it as a function. Last time we found the derivative at any point a. So we had our formula over here, and we used as x is a and x is a. And that gave us the derivative at that value of a. Remember, that's the same thing as the slope of the tangent line and instantaneous rate of change and all those words that we learned. So that gave us a slope value. But what if I want my derivative to be really just another function in terms of x so that I can plug in any value of a that I want? So that's going to be really helpful to just take a general derivative in terms of x and then later plug in any value that you want. What's f prime of 1 or negative 2 or f prime of 100? So it'd be really helpful to have a function for all values of x that we can plug in. So notice that we're going to use the same formula that we had last time, but notice that instead of a, it is in terms of x. This is, for those of you pre-calc fans, this was the official difference quotient from last year. So this is going to be in terms of x. Your answer will be in terms of x, and then we can plug in any value you want. Okay, the f prime of a that we did last section is good. It's very helpful, but moving forward, we're probably going to be using this formula more often to get a general idea of the derivative. Now, how else can you notate it? Remember, we learned f prime of a or f prime of x. But remember, because f is the same thing as y, then f prime is the same thing as y prime. We see this one sometimes. Because the derivative is the change or instantaneous rate of change, we use d's for derivative. And so we see dy dx, or some places put the delta triangle, delta y over delta x. That's more of a science physics thing, but that does stand for the change in y over the change in x. But dy dx, you can think of the d as being derivative. This one is actually really, really popular. The derivative of y with respect to x is dy dx. So if you ever see dy dx, that's a pretty new one. Put a star next to that one. That means the derivative. That means the same thing as just f prime of x. But again, because f is the same thing as y, I can change the y here and plug in d and then just have the function. D, the derivative of the function with respect to x. So d dx of f of x. These last two are not very popular. You'll see those maybe in sort of college calculus classes, but again, the capital D mean derivative, the derivative of f, or the derivative of f with respect to x. But don't worry too much about these last two. I rarely see it, especially not on the AP test. In order, really, f prime of x is probably the most popular here in the front. dy dx is probably the second. Just taking d dx of the function, and then y prime. But these first four are the most important. Why don't we practice? All right, given my function, here's my beautiful parabola function. Can you find, there you go. That tells you right away I want the derivative with respect to x. So I'm going to use the new formula up here, and it's going to be x instead of a. All right, it's going to be more algebra, a little bit more just letters and variables, not many numbers, but the same steps. Let's try it. All right, I'm going to need a little extra room here, so I'm going to take this and put it on a separate page. All right, f of x let me just double check, make sure I picked the right one. Yep, 3x squared minus 4x plus 2. And I want to find the derivative. So find f prime of x. Okay, here we go. The derivative f prime of x is the lim, as h goes to 0, of our difference quotient, but now in terms of x, no a's. There you go. All right, let's plug in our function. F of x plus h would be 3x plus h squared minus 4, not x, but x plus h plus 2. Okay, that's just f of x plus h. And then we ran out of room, so underneath I'll put minus f of x. And when you subtract here, folks, before it was f of a, so it's just a value, but because you're subtracting a function, please Big parentheses, always, always. Otherwise, things just won't cancel and we'll get a lot of algebra mistakes. So a little star off to the side, always put parentheses around your f of x when you subtract. All right, he's going inside. That's just our regular function, right? How about 3x squared minus 4x plus 2? And the whole thing all divided by h. All right, so, if we tried to do a limit here, try to plug 0 in for h, of course we couldn't do it. So the next step is to just do all of this algebra and see what we get. Here we go. So this becomes the limit. All right, let's start foiling everything and then multiplying by 3. So if you want to go ahead and do all the algebra yourself first and then catch up with me, I'm going to jump right to the next step, folks. Here we go. After foiling and multiplying by 3, I should get 3x squared plus 2xh, but you're multiplying by 3, so 6xh, plus h squared times 3 again. Okay, there's the first piece after foiling and distributing by 3. Then we're going to distribute the negative 4. And now I can release those red parentheses, but I have to distribute the negative sign, right? Good job. That's all divided by h. Still can't plug in 0 for h. But look, now we have. If we do it right, a lot of things should cancel. And for those of you who've done this a lot, you probably notice that it's always the f of x terms always cancel somewhere in the previous part of the expression. So I'm going to look to really cancel the negative 3x squared right away because that's going to go. And yep, here it is. Poof, gone. How about the positive 4x? Yep, here it is. Poof. And then negative 2, gone. Positive 2, poof. Okay, so now let's see what we're left with. This should be the lim as h goes to 0. All right, leftovers. We have 6xh, 3h squared, and hidden inside there you see a 4h. And you did it right if you see an h in every single term, because you want that to cancel and divide out with the h on the bottom. So we did it right because there's an h everywhere. In fact, let's go ahead and factor out that h so we can see it cancel beautifully. We're left with a 6x plus 3h minus 4. Great. All right, now that you factored the h out, can we get rid of them? Let's do it. Boom. Boom. All right, leftovers. Leftovers. How about 6x plus 3h minus 4? Phew. All right, now can we plug in h equals 0? Yes, the denominator is gone, so now you can plug in h equals 0, and this guy goes bye. And let's see what you're left with. This becomes, the limit's done, we'd have 6x minus 4. And you just found for yourself, folks, the derivative of the function f in terms of x. So now if you want to find what is the derivative at 2, oh, dude, plug in 2. What's the derivative at negative 1? Oh, plug in negative 1. And you don't have to keep using the formula with f of a plus h over and over and over. You've got this. This is set in stone, and you can plug in anything you want. Good job. How's that first one? Is that okay? Now, I know the second one's a little bit tricky with the algebra, but I just want to set it up with you so to make sure you know what it looks like. But this is a rational expression, which is really terrible to find the derivative the way we're doing now. God bless the shortcuts when it comes up, and we'll learn a faster way to do it. But look what it's asking us to find. Look at that notation. That's the derivative of the function. So again, it's the same thing as f prime of x. Ready? Let's set it up. So this is going to be the limit as h goes to 0 of, f of x plus h here is going to be pretty massive because it's a fraction within a bigger fraction. Okay, this is going to be, let me change colors so we can see. Just the f of x plus h would be 2 minus x plus h over 3x plus h plus 1. That's just f of x plus h. Can you see that? All the x's got replaced with x plus h. And then we're going to subtract the original function, 2 minus x over 3x plus 1. And that whole thing is still being divided by the h that was in the denominator. Look at that. Look how terrible that looks, right? It's a complex fraction. So we have a fraction and then a fraction. And this is really, really hard to simplify algebraically. We'd have to find a common denominator on the top. We'd have to multiply by the reciprocal. Oh my gosh, I'm thinking this. So luckily, in another couple of sections, we're going to learn all the shortcuts. And if you have a rational expression, the derivative has a really, really cool shortcut. So for now, I'm going to stop because I just wanted you to see what the setup looked like so you feel like you understand what this new formula does. Okay, but let's move on. Good job. Now, looking at graphs of derivatives is going to be really important for the AP as well. If I give you a function here, here's f of x, beautiful continuous function. Can we draw the derivative graph? And remember, the derivative graph is just the slope of tangent lines, right? So what you want to think of is just take points along this curve and mentally, or actually physically if you want, draw tangent lines to all those points. Estimate the slope of those tangent lines, and those are the new derivative values. Because remember, slope equals derivative. So if I'm trying to find the derivative graph, I'm trying to find the y values of the derivative graph, I'm going to be using the slope values of the tangent lines to get those y values. Okay, let me give you a really cool shortcut. Anytime you're graphing a derivative, always look for the bumps of the original function. The max and mins, basically. Why? Think about it, guys. If you're trying to find the derivative at a bump, ready? Let's draw a little tangent line at that bump. What's the slope of that line? How about the next bump? Tangent line. What's the slope of that line? And the last one. I'm going to repeat myself. What's the slope of that line? Do you notice that all of these slopes equal 0, right? So that's going to be the y value on the derivative graph, right? Because the derivative is 0, so the y value of the new graph is going to be equal to 0. So at that x point, I think the x point was right about here, right? The derivative would be equal to 0. So this point would be on my derivative graph. I'm going to have my derivative graph in red. Okay, so at that x value, the slope of the tangent line on the bump was 0. So my y value is 0. The next bump was right about here. So that x value is there. So the y value is 0. And the last bump was over here. So those three red dots are derivative values, aka slope values, at the tangent lines of the original graph. So those are going to be the points on my new graph. Now what we're going to do is just estimate as we walk along the graph left to right. Let's pick some more values. I'll pick maybe that value, maybe this value. And again, we're just estimate. This doesn't have to be like a Picasso painting or anything. We just want to estimate the slopes. Okay, so going left to right, guys, if I look at this first line, I say, hey, what's the slope of that line, do you think? Is it positive, is it negative? Well, it's going downhill, so I know the slope is definitely negative. And, is it like 1 or is it greater than 1? Meaning, like, is it negative 1 or negative 2? And if I remember, we've talked about this a little bit in class. If the slope of a 45-degree angle line is 1, right? Because on that line, you're going up 1 over 1, up 1 over 1, up 1 over 1, right? That's a 45-degree angle. So the slope of a 45-degree angle is always equal to 1. And also, if you go negative 45 or down that way, that's also going to be a slope of 1, but it's negative. So keep that as your reference here, friends, that a 45-degree angle of a line has basically a slope of 1 or downwards of negative 1. So let's go back to this line over here. It looks like he's a little bit steeper than negative 1, so I'm going to think that slope is maybe like negative 2. So that's going to be the y value at that x location, so maybe down here. So that's going to be a slope of negative 2, which means my y value on the derivative graph is negative 2. Let's keep going. The next point I drew was this one. Okay, what's the derivative slope? Well, it looks like maybe that slope is about a positive and maybe about a positive 1. So at that x value where I drew the yellow dot, the derivative or the new y value should be about there. You getting the hang of it? Let's try one more together and see if we can do the rest. Here's about the tangent line of the next one. So at that x value, it looks like, again, my slope is negative, and it looks like it's even steeper than the first dot that we drew. So I'm going to think maybe even lower than negative 2, maybe like negative 3 down here. Okay, so I'm going to keep on going and maybe draw at the next one. Again, pretty steep, but maybe not as steep. And then we had this one where the slope was 0. At that next y value, the next point I drew, slope, positive, maybe about equal to 1, so maybe about. And the last one, positive slope, bigger than 1, maybe up here. Okay, so I'm going to take all my red points, I'm going to connect them. You can see it makes a kind of a neat little polynomial here. That's a really good estimate of the derivative graph. So the big clue was, think of tangent lines everywhere. Hit the bumps first, because the bumps have derivative that are horizontal lines, or slope equals 0. So do those and graph those first. Those turn into basically roots or zeros or x-intercepts. And then just really go just point by point and imagine positive slope of the tangent line or negative slope and graph those new y values. We'll do a couple more of those in class too as well. But just to sort of verify, look how the graph on the left has a derivative on the right. And you can verify that really by just, taking a couple values here. Look at that slope. That's a really small positive slope, maybe equal to like a half. So that's why the y value in the derivative is equal to a half. As I go up, the slope is becoming less steep. It's still positive, but it's getting really, really, really close to 0. Look at that. Versus if I start working my way backwards, look at these slopes. They're getting higher and higher. Really steep, really positive. And look what happens. The y values, aka the slope values or derivative values, are getting higher and higher. How about over here? The derivative of this is this graph. Right? And we can verify that. Look at the bumps. There's a bump here at a little bit to the right of -1. So look what we have there. Look, it's a 0. Right there's another bump. And on the derivative graph is a 0. As we approach it from the left, look how my slope is really positive, and that's this whole region over here. As we pass the first bump, it's now negative slope, so my y values are negative down here. And then we end with positive slopes, and that's my y values are positive over there. So it makes a lot of sense that this graph, when I take the derivative and take all the slope values, I get this graph here. Pretty cool. All right, shall we give it a try? For number 1 here, you're given a graph on the right-hand side. This is your original f of x. I want you to graph the derivative, but I want you to walk through the steps. I want you to do parts A and G and find what the slope values or derivative values at each of those x points are. Graph those new points, and we'll connect them into a final derivative curve. Go for it, friends. Go ahead and pause the video, try it, and I'll catch up with you in a second. Okay, you ready? Here we go. F prime of -3. That's the slope of the tangent line at x equals -3. And when I go to x equals -3, my point on the graph is this. My tangent line is about this, which is negative, but not quite as negative as a 45-degree angle. So it's not quite -1, maybe a little bit less. I'm going to say, and again, this is just estimate, right? So you can be a little off. It's okay. Let's say it's like -0.5, -0.5. Okay, that will give me a point. At the same x point of -3, I would get a y value, which is the slope of -0.5. Okay, how about at -2? My point on the graph is right here. So my slope is right about there, which looks really, I didn't draw that tangent line very well, sorry. But it looks almost like 0. I would give that a 0 or so. Again, we're just estimating. So at x equals -2, my derivative graph should have 0 for the y value. Let's keep going. -1. -1, this point is right there. Slope is there. I'm feeling that's pretty close to a 45-degree angle, so I'll say that's about equal to +1. Okay, so therefore, cool. And if you keep going and keep going, at 0, I'm going to do one more with drawing the point in the line, and I wonder if you could do without me doing that. Okay, at 0, here's your point. Slope is greater than 1, I think, but not much, but greater. Maybe, shall we say 1.5 or 1.5 or 3/2, all same. Okay, now I'm not going to draw the point or the tangent line. Can you imagine it? All right, at x equals 1, thinking on the graph, I see the point. The y value right now is 1.5. And if I draw that tangent line, it's pretty close to 1. It's not as big as the one before it. It's not 1.5. So I'd say about 1. At f, the derivative at 2, I'm looking at the slope. The y value is 2. I'm imagining the tangent line. I think the tangent line is pretty horizontal, don't you think? So a horizontal line always has a slope of 0. And finally, at f prime of 3, the derivative at 3. All right, on my graph, looking at x equals 3, the y value is like 2.8 or so. That tangent line is now going to be negative, but very, very small negative. So maybe a half negative, or a third or a fourth, but definitely small, not quite -1 yet. All right, friends. So if we graph these together, we get something like that. And if we see the original look like this, there we go. That's a really good estimate of f going to f prime of x. Okay? Again, notice we did the bumps. And actually, we didn't do the bumps first just because we're asked to do it in this order. But if you're ever just given a graph and you want to find the derivative graph, do the bumps first because those are your x-intercepts. All right, let's take a break from the visuals. Great job, guys. Let's go back to the algebra. Now, because we take the derivative and we get f prime out, f prime is a function, right? It's in terms of x. So we could always just keep going. What if we found the derivative of the derivative? Ooh, sweet. What happens? Well, you're taking the derivative of the derivative. So that's f prime of x prime. Or look at the notation. We have two prime symbols there, f double prime. Or we can just write it as f double prime. And we say literally that's f double prime. That's the second derivative. The second derivative is f double prime. Oh, cool. So for example, let's find this. If f is x cubed minus x, can we find the second derivative? Interpret just means, let's figure out what that means graphically. Okay, this is going to be a little bit tough because it's x cubed. And in order to find this friend, we have to find the first friend first, right? So let's go through the steps and we'll find the first derivative and then we'll take the derivative of our answer and get the second derivative. Okay? Oop, I don't look at the graph yet. Okay, I'm going to need a lot of space for this one, folks. And you will too. So let's make some space. X cubed minus x, right? All right. Okay, so our goal in your brain, you want to find the first derivative and then take that and find the derivative of that to get the second derivative. Okay, here we go. The lim, as h goes to 0, of f of x plus h, not the a plus h, that's the old one. This is now the function version. So x plus h would be x plus h cubed minus x plus h. Cool. And let's subtract our original function, f of x. Oh, whipping out the parentheses, Mr. Brown. How about x cubed minus x all over h. Now, what makes this hard, like I mentioned before, is we're going to have to FOIL this. It's this cubed, so you have to FOIL it twice, basically. Luckily, again, when we learn the shortcuts, we don't have to FOIL this many times. It's very rare that we see an x cubed that we actually work out by hand. Most likely, you'll do x cubes using the shortcut. So we'll do it once. Let's just get it out of the way. Oh, here we go. Ready, ready. Now, we do have a formula for cubing things, if you remember way back from Algebra 2. So I'm going to show you that. Or you can just do it by hand. But this is going to be x cubed plus 3x squared h plus 3xh squared plus h cubed. It was like a combination of Pascal's triangle and the binomial theorem, or just literally the formula for cubing something. If you don't remember, friends, don't worry about it. It's okay. You can just FOIL it out by hand. But again, this will probably be the last time you're going to have to FOIL it out by hand because we'll use the shortcuts next time. Okay, less talking, more deriving. All right, looking pretty hot. All right, take a breath. Now, let's see what's going to cancel. How about the x cubed? Poof, poof. And the x? Poof, poof. And remember we said, you did it right if you have h's in every term that's left in the numerator. How about 3x squared h plus 3xh squared plus h cubed minus h. Everything has an h, which is beautiful. Okay, let's factor out that h, friends. Let's see what we get. H. Oh, did I ever tell you that, we couldn't plug 0 in, right? That's why we're doing all this algebra. Okay, good. Back to math. 3x squared plus 3xh plus h squared minus 1 when you factor out the h from the last term, right? Okay. Glad you agree. All right, let's kill these h's on the outside. Oh, poof, poof. Awesome. Who wants leftovers? I got 3x squared and everything. Now, can we plug in h equals 0? No, I'm gonna. But I'm going to plug it there and there. And because the h is 0, it's going to destroy this whole term. Bye! And then h squared is 0. Bye! And I'm telling you now, my lovely friends, that the derivative of x cubed minus x is dun, 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 dun. Yay. Okay, that's the first derivative. Oh, well done. Are we done? No, we got to do the second derivative. Okay. Again, God bless the shortcuts when we get there. But it is really important that we have to learn this way with the x plus h because it does appear slightly on the AP. And I'll explain that later, but it's not too much. So we're going to use shortcuts most of the time. Ready? Here we go. Let's do it again. F of prime of x is 3x squared minus 1. All right, let's do the second derivative. You want to do it first? You want to beat me to it? Here we go. The second derivative. A whole new limit that we're going to start, and we're going to do f of x plus h. There we go. And subtract 3x squared minus 1. Oh, Mr. Brown, did you use parentheses? Yeah, I did. Did you? I bet you did too. Here we go. Limit as h goes to 0. All right, let's FOIL it out. Let's multiply by 3 afterwards, and we get 3x squared plus 6xh plus 3h squared minus 1 minus 3x squared plus 1. Whew. All right, take a breather. Let's see what we're going to destroy. The ones. See ya. Negative 3x squared and positive bye. Leftovers. Every time I say leftovers, I get a little hungry. H goes to 0 of 6xh plus 3h squared over h. Now, some of you are doing this, I've noticed in the homework, and this is fine. You notice that you can cancel the h because you have h everywhere, so you just do this. Bye, bye, and bye. That's actually fine. You'll get the same answer. Just make sure you are canceling from every single term. And if you had something like a plus 4 hanging out here, you know that you can't factor an h out of there. So there's something wrong. Something wrong happened. You have to have an h everywhere. So just be really careful. Okay, I'm going to be Mr. Brown, the teacher, and I'm going to factor an h out just because that's what I do. That's how I roll. Take out h. 6x plus 3h. You see the h's on the outside? Yeah, they're gone. This becomes a lim of 6x plus 3h. Now h is going to 0. Here he goes. He goes to the past. He goes long. Poof! He's gone. And your second derivative, lovely friends, is 6x. Phew. So the original function was, if you remember, x cubed minus x, which is a cubic function. We're going to see that visually in a second. The first derivative is a parabola, and the second derivative is linear. When you have normal polynomials, folks, you'll notice that when you take the derivative, what often happens is you go down a degree. 3 cubed, x squared, and x to the 1. That happens with most polynomials. Let's go back and see what happens on the graph. Ready? Look at that. Here's our original function f, cubic. Our derivative was a parabola shifted down 1. And our second derivative was a linear line with a slope of 6. Look at that. So it seems like it goes down a degree each time. We're going to also notice that if you take the original function, look at bumps. Look how the bumps refer to zeros on the other graph. And look at the pink graph. Look how the bump on there refers to the green 0 here. All right, good job. We got about half it done. More to come soon. See you in the next video, folks. Great job today.